Hey everyone! In this video I'm going to introduce the idea of generalized linear models and explain how the models that we already talked about, linear regression and logistic regression, are basically special cases of GLMs. Okay? So what are GLMs? In general, generalized linear models all share a couple of components that we already discussed in previous weeks. Okay, the first component of any GLM is a vector of outcome data, which we usually call y. And this is basically just the data that we want to predict. Okay, we want to create predictions for either a new data set or, in the context of causal inference, predictions for counterfactual and so on. Okay, so we always have some outcome data y. Okay, we also have a matrix of linear predictors, which we call x, as well as a vector of coefficients, which we usually call beta. Okay, both combined form the linear predictor x times beta that we have seen both in linear regression and logistic regression. Okay, now the important thing is that we have a link function, and we introduced that idea in the context of logistic and probit, logit and probit models. Okay, and this link function g basically transforms our linear predictor into our y hat, so into basically a prediction, either a probability or some other kind of transformed data that we can use for prediction. That we can use for prediction in the end. Okay. We need this y hat because ultimately this y hat is needed to create predictions from our data distribution. Okay, so we have some kind of probability distribution P. This could be, a Bernoulli distribution or a binomial distribution or a normal distribution for linear regression, where our observed outcome y has a certain probability or a certain density conditional on our transformed data or our transformed linear predictor, right? So again, in the logistic regression case, this was our predicted probability pi, and we can basically compute the probability of observing a 1 rather than a 0, based on the predicted probability. Okay. There are other components that can be part of this data generating process. For example, we can model variances over dispersion, different cut points, depending on the underlying model, that are ultimately all involved in either the predictors or the link function or the underlying data distribution. Okay. But all GLMs ultimately share these components. That we have some outcome data, we have a linear predictor, x times beta, right? We have a link function that ultimately links the linear predictor, which is always, bound between, it's continuous and bound between minus infinity and plus infinity theoretically, to, some kind of prediction that we actually care about in the context of our outcome measure. For example, a predicted probability for the dichotomous case. And then we have an assumed data distribution, like a normal distribution, or Bernoulli or binomial, and so on. Okay, so these are all components of the GLM. And so how can we model or predict outcomes using generalized linear models? And the strategy that we're following is basically always the same. Ultimately, what we're doing is we have an outcome that we want to predict, and what we have to do is we have to formulate a suitable probability model for the data generating process. Okay, so essentially we have to make decisions about how we want to basically set up our linear predictor and our link function and ultimately our data distribution to represent the kind of theoretical unobserved data generating process that basically from a theoretical perspective, we think kind of produce the data that we actually observe. Okay, so in order to do that, we need to make assumptions about the distribution of y. So that's what we refer to as the stochastic component in the past. Okay, so this is all assumptions about the underlying data distribution. And we need some parameterization of the estimate, so the systematic component, right? So this is basically focusing on this linear predictor as well as the underlying link function, basically linking the linear predictor to our data distribution. Okay, so basically, once we have that, once we defined our underlying probability model, the stochastic component and the systematic component, we can derive our log likelihood, we can specify our prior distributions, and ultimately estimate the model, right? And this is a general framework that we can use not only for continuous normally distributed data or dichotomous, Bernoulli trial data, so to speak, but we can use it essentially for any type of outcome measure that we're trying to predict. The only thing is that we have to, adjust our link function and adjust our data distribution in order to then, predict our outcome measure. Okay. Ultimately, after we estimated our model, we can summarize our results as well as the underlying uncertainties, particularly estimation uncertainty, by simulating quantities of interest based on draws from the posterior distribution, at least if we're working in a Bayesian framework. If we're working in a frequentist framework, we can kind of make additional assumptions about the sampling distribution and simulate as well. But at least in the Bayesian framework, we have the added convenience of directly being able to use the posterior distribution samples. Okay, and then we can make predictions. We can convey our uncertainty, as we talked about in the linear regression and logistic regression framework, and then we can also check whether our model ultimately fits the underlying data structure. Okay, we talked about techniques like posterior predictive checks and so on, and all these kind of techniques that we talked about in detail for those previous models, they all kind of apply in the same way for generalized linear models as a whole, right? So basically, what we'll do going forward is talk about different types of models fairly quickly. I'll just provide a brief overview, but you can kind of refer back to a lot of the techniques that we've seen for logit models and linear models, and you can apply the same techniques, the same code, the same kind of arguments regarding visualization strategies and so on to your specific outcome and your specific model for that outcome. Okay, so essentially we now have a general strategy of how to kind of address any type of outcome that we might encounter for our predictive task. All we have to do is come up with a matching data distribution that represents the underlying data generating process and a link function to ultimately transform our linear predictor. Okay. So with this framework at hand, we can basically now go to our substantive area of research and address any possible outcome, well, with some restrictions, of course, but we have a general framework that we can that is flexible enough to ultimately model a wide range of possible outcome measures. Okay. So to give you a little bit more of an overview of what this will look like going forward. Oops, that is not what I wanted to do. This is what I wanted to do. So as I mentioned, we have different types of outcomes that we want to predict. Those are ultimately produced by different types of data generating processes. And ultimately, depending on the underlying data generating process, that we, of course, have to kind of think about from a theoretical perspective. We can't really observe the data generating process. But depending on kind of our theorized data generating process, we have to specify different types of link functions and different types of data distributions to ultimately kind of come up with a predictive model. Okay, and there are a couple of standard types of outcomes that we can think about, and where different models have been developed with advantages and disadvantages in modeling these types of outcomes. Okay, so to give you a little bit of an overview, we already kind of talked about continuous outcomes and particularly normally distributed or not necessarily normally distributed, but in many cases normally distributed continuous outcomes where the underlying link function in the linear regression framework is of course just the identity. So our linear predictor is equal to the conditional expectation in the linear regression framework. There's no additional logistic transformation or anything like that, right? And so the underlying model here that we talked about at length is a linear regression, and depending on the assumptions that we make, if we assume normally distributed IID errors, then the underlying data distribution is also normal. Okay. Of course, we also talked about deviations from that assumption, but at least in general, that would be kind of the data distribution that we could assume. Okay. We also talked about dichotomous outcome measures, so just binary 0 or 1 outcomes, turnout, voting in US presidential elections, and so on. Here we have different types of link functions that are available to us. We talked about the logistic link and the normal or cumulative normal distribution, which again, from a substantive perspective, yields kind of the same predictive inferences, but ultimately leads to different coefficients due to the different types of link functions. And depending on the link function, we end up with a logit or a probit model. Regardless of whether it's a logit or a probit model to compute the predicted probabilities, ultimately the underlying data distribution, since it's a dichotomous outcome, is always just a Bernoulli trial, essentially. Okay. So those are the two types of outcomes that we already talked about, and now we're going to expand that tool set. We're going to talk about counts, where usually we will use a logarithmic link function in order to bound our linear predictor or the transformed linear predictor to be only positive. So we take the exponent of our linear predictor usually. And there are different types of models and data distributions. Usually we can model count data using either a Poisson distribution or a negative binomial. And I'll talk about the differences between those two in the next video. We can also model the number of successes from out of a set number of trials. Okay, this is different from counts because counts essentially are not bound. They don't have an upper bound, right? You can basically count up to infinity theoretically, but if you count the number of successes out of a set number of trials, where the number of trials differs between individual observations, then that's a slightly different data generating process. You can model this using a logistic binomial or a beta binomial, depending on whether you have overdispersion. We can also think about ordered categories and unordered categories with more than two outcome categories, so to speak. Okay, those are basically extensions of the logit and probit. One, we have the ordered logit and ordered probit, where we have just multiple categories, but they have an inherent ordering to them, and we're going to talk about those in one of the videos that is coming up. And then we have unordered categories, where we again have multiple categories but no inherent order between them, and we can model those using multinomial logit and probit. Okay, so this is kind of just a brief overview. There are additional kind of extensions and other types of models. For example, we can include kind of robust regression models, where we make additional distributional assumptions to allow for more extreme cases to occur. In the textbook, there's a little chapter on that in the context of logistic regression, for example. We can also, extend the data generating process or extend the model to include kind of predictors for variances to model heteroscedasticity. We can think about changing asymptotes in logistic regression. We can mix discrete and continuous data, for example, to take into account censoring or selection, or we can model durations and kind of event history model data. Okay, so there's a huge kind of set of different models and different kind of tools that you can use for your specific substantive research area. Obviously in this course we can't go through each individual model in as much detail as we did for linear regression and logistic regression. The key here is to understand that they all kind of follow a similar structure, the strategy, the underlying strategy in kind of modeling the data generating process using different link functions and different data distributions is always the same, right? And the way we kind of ultimately compute and simulate quantities of interest and evaluate model fit is also always the same, right? So it's always, or it's more important to kind of get an understanding of the general idea of how to address different types of predictive tasks, rather than thinking about these as just different tools in your toolbox, right? The underlying principle is the more important thing to understand. Okay, so much about kind of the overview of generalized linear models as like a broader category of models for different types of outcomes with different data distributions. In the next couple of videos, I will kind of showcase just a few of those examples, and specifically, we're going to talk about modeling count data, modeling ordered categories and unordered categories. Okay, we can talk a little bit about other types of models going forward, also specifically in the context of your replication study. If there's any additional kind of type of model that you would be interested in, we can address those in the Q&A session, or maybe in one of the upcoming weeks as well. Okay, so much for our overview. In the next video, I'm going to talk about modeling count data using Poisson and negative binomial regression.